In this section, we're going to continue talking about pH calculations, but we're going to look specifically at different combinations of weak acids, weak bases, with strong acids and strong bases. Let's start with an example. 20 milliliters of 0.5 molar acetic acid is titrated with 0.250 molar sodium hydroxide. Ka is 1.80 times 10 to the minus 5. We're also shown the reaction of the acetic acid with the sodium hydroxide to produce sodium acetate and water. Several parts to this question. Part A, what is the pH before any titrant base is added? What is the volume of the base required to neutralize the acid? What is the pH after 10 milliliters of sodium hydroxide is added? What is the pH after 20 milliliters of sodium hydroxide is added? What is the pH at the equivalence point? And what is the pH after 50 milliliters of sodium hydroxide is added? Okay, so in part A, we're asked, what is the pH before any titrant base is added? So this is zone 1, before any titrant is added from the burette. So the only thing we're focused on is the 20 milliliters of 0.5 molar acetic acid, right? Since acetic acid is a weak acid, what we're basically talking about here is weak acid dissociation, and we can calculate that first. So this equation is showing the dissociation of the acid. When you add it to the water, you get H3O plus and CH3COO minus, the conjugate base, right? That's what is initially in the flask before adding any base. Okay, so let's start by thinking of what are our initial amounts, what's the change, and what is our equilibrium amounts, so that we can use our calculations over here, keeping in mind that for a weak acid dissociation, we can write a Ka expression, CH3 COO minus, concentration times H3O plus, concentration, so products over the reactant CH3 COOH. Okay, so start there. Now, what's the initial concentration of the acid? We're told it's 0.500 molar, and we initially have no dissociation. Then there's some change, right, where we dissociate some of the weak acid and form the H3O plus and the conjugate base. And so at equilibrium, we have 0.500 minus X, and then each of these are X. So if I put each of these in for concentration of CH3COOH and concentration of H3O, that's where this X squared comes from. And then on the bottom, we just have the concentration of the CH3COOH. And as we've seen in the past, we can assume that this X is very, very, very small relative to the initial concentration. So we can simplify our Ka expression to be just the concentration of the CH3COOH. Then we rearrange here to solve for X squared. Ka is given in the initial problem, 1.8 times 10 to the minus 5 times 0.5. And then the square root gives X equal to 3 times 10 to the minus third. Now, what does X equal? X equals this acetate concentration and this H3O plus concentration. So we can use that to find the pH, right? pH is the minus log of the hydronium ion concentration, 3 times 10 to the minus third, which gives us a pH of 2.52. All right, now that we've done our zone 1 calculation in part A, in part B, we are asked what is the volume of the base required to neutralize the acid. So remember that neutralization happens at the equivalence point, or zone 2. I've shown for reference the overall reaction between acetic acid and sodium hydroxide. And I've shown the net ionic equation because the sodium ion is a spectator. So overall we have acetic acid reacting with hydroxide, and in solution at the end we have water, right? There's the neutralization to form water, and then we have acetate ion left over. So to calculate the volume of the titrant needed to neutralize the acid, we're finding the volume at the equivalence point, and that's needed to establish our titration zones. We already talked about zone 1, the beginning. Zone 2 happens from the start to the equivalence points. We need to know where the equivalence point is first. So let's start with MAVA equals MBVB. We have a monoprotic acid and a monobasic base. So this is a direct relationship. And we can solve for the volume of the base that is required and then substitute the values. So for the acid, 20 times 0.5, and then the volume of the base is what we're solving for. And the concentration of the base is 0.250 molar. So that's just a quick computation, and we get 40 milliliters. So after the addition of 40 milliliters, the base has neutralized all of the acid. Part C is where things get interesting. So the question is, what is the pH after 10 milliliters of NaOH is added? I've kept the overall reaction and the net ionic equation here for reference. But let's think about what's going on. If only 10 milliliters are added, this is zone 2, because the 10 milliliters of base, the titrant that is added, is less than half of the 40 milliliters that we calculated to reach the equivalence point. So we're early on in the titration here. We're not even halfway to the equivalence point. By the way, that's a special term. The halfway point, after I add 20 milliliters, that halfway point has a special name. It's called the half equivalence point. All right, so think big picture with me here. If I'm not at the equivalence point, that means I have some amount of acid and some amount of base in the flask, but those amounts are not equal because I'm before the equivalence point. At this point, I'll have more acid than base, right? In order to calculate the pH, I need to determine what concentration of acid do I have at that point. So we're going to start by doing some stoichiometry of the neutralization reaction. So find out how much of the acid does 10 milliliters of the base neutralize, and therefore how much is left. So let's first calculate the initial moles. So the initial moles of the acetic acid will just be the concentration times the volume of the acetic acid. Same thing for the NaOH. The concentration of the NaOH and the initial volume of the NaOH that's added. So I'm just substituting here. Let me use a highlighter. It might be a little easier to see. So the initial concentration of the acid multiplied by the initial volume of the acid. Same thing for the base. The initial concentration of the base multiplied by the volume of the base added. Okay, so that gives us our moles of acid and our moles of base. Okay, from there we can set up an ice chart. Okay, so again, this is our neutralization reaction. Our initial amount of moles of our acid, 0.0100 or 1 times 10 to the minus 2. Our initial moles of the hydroxide, 0.0025 moles. And our initial formed moles of product, 0. So again, I just want to point out here, I can quickly reference the net ionic equation. The sodium ion is a spectator, right? That's why I haven't included it here as a product. Okay, so what is the change? Well, all of the hydroxide reacts because we're before the equivalence point, right? So there's enough hydrogen ion to react to use up all of that hydroxide. So the change is a decrease of 0.0025 moles of hydroxide. That's how many moles of the acetic acid reacts. And then what are we left with at the end? 0.00750 moles of acetic acid and 0.00250 moles of the acetate ion are formed. The total volume of the solution at this point is 30 milliliters. Keep in mind, we started with 20 milliliters of acetic acid and we added 10 milliliters of NaOH to it. Once we know the number of moles and the total volume, we can find the new concentrations once that new equilibrium is established. So that's what I've done here. For the acetate, the moles we found was 2.5 times 10 to the minus 3 divided by the volume, 30 milliliters or 0.0300 liters. So the concentration of the acetate ion at equilibrium is 0.0830 molar. And for the acetic acid, the moles that we calculated were 7.5 times 10 to the minus 3. In 30 milliliters or 0.030 liters, we get 0.250 molar. All right, so the solution that we have is a buffer. We have some concentration of acetic acid and some concentration of the acetate ion. The salt produced contributes conjugate base as common ions. So we could use a Ka expression to find the pH, but if you remember from our unit on buffers, we could use the Henderson-Hasselbalch equation to solve for the pH of the solution at this point. So that's pH is equal to pKa plus the log of the base concentration over the acid concentration, or the negative log of the Ka, which is given, plus the log of the base concentration over the acid concentration. We calculated these on the previous slide. Remember, it was moles over liters, given that the total volume of the solution is 30 milliliters. And we get a pH of 4.26. All right, now in part D, we are asked, what is the pH after 20 milliliters of NaOH is added? So in part A, it was calculated that 40 milliliters of NaOH was required to completely neutralize the acetic acid. The 20 milliliters of NaOH exactly neutralizes half of the acid, leaving 20 milliliters of acid and creating an equal number of moles of the salt. This is still zone 2. So before any neutralization occurs, I have 0.0100 moles of acid and 0.00500 moles of base. And before any neutralization occurs, I haven't formed any acetate. Remember that before the neutralization point, the weak acid in this case will neutralize all of the base. So all of that is neutralized. And in doing so, we use up some acetic acid and produce the conjugate base, the acetate ion, so that we have 0.0050 moles of acid and base. Now this is our moles. Remember, we get that by multiplying volume times concentration, okay? And we're going to find these new concentrations on the next slide, keeping in mind that the total volume is now 40 milliliters. So to find the concentration as the equilibrium is reestablished, we take the number of moles that we calculated on the previous slide, and it's equal for acetate and acetic acid, 0.0050 moles, but now it's in 40 milliliters or 0.040 liters. So we have a concentration of 0.125 molar for the acetate and 0.125 molar for the acetic acid. So these concentrations, these are our equilibrium concentrations, and they'll become necessary to determine the pH. All right, so the solution has equal concentrations of acid and its conjugate base, creating a perfect buffer. This is a perfect buffer where the ratio of base to acid is 1 and the pH is equal to the pKa. This is known as the half equivalence point. The amount of acid left in the flask is equal to the amount of conjugate base. So these two concentrations are equal, which makes this 1, and the log of 1 is 0. So when that happens, the pH is equal to the pKa, or in this case, 4.74. All right, so now finally in part E, what is the pH after 40 milliliters of NaOH is added? So in part A, we did the work of calculating that 40 milliliters of NaOH was required to completely neutralize the acetic acid. So that means this is zone 3, the solution at the equivalence point. So take a look at what happens here. So 20 milliliters times 0.5 molar acetic acid gives us 0.0100 moles of acetic acid. 40 milliliters of 0.25 molar NaOH gives us 0.0100 moles of OH minus. All of the OH minus is consumed. All of the acetic acid is consumed. And in doing so, we form 0.0100 moles of the acetate ion. In this case, the total volume of the solution is 60 milliliters. So at this point, what's in the reaction vessel? It contains sodium ions and acetate ions only. The acetic acid is completely neutralized, and so are the hydroxide ions. All right, so let's find the concentration of those acetate ions. Take the moles calculated in the previous slide, 0.0100, and divide by the volume, 0.0600 liters or 60 milliliters. We get a concentration of 0.166 molar. So that's our initial concentration of acetate ions. And remember that there's this equilibrium that's reestablished where the conjugate base, the acetate ions, undergo hydrolysis in the solution of water, okay, where some tiny fraction of OH minus and acetic acid are formed, and we call that X. So because the acetate ion is the conjugate base, we can't use this Ka directly. We need to find Kb, which is K water, 1 times 10 to the minus 14 over the Ka provided, 5.56 times 10 to the minus 10. Think of a Kb expression. No, don't think of it. Remember that it's OH minus CH3COOH over the acetate ion. Right? Now, these are both X, which is where we get X squared over, remember the change is very small here, so we just assume the initial concentration. That allows us to find X, which relates to the hydroxide concentration. So we can find the pOH of 5.2, and that means that the pH is 8.98 at the equilibrium point. F. What is the pH after 50 milliliters of NaOH is added? So this is zone 4, as the 50 milliliters of titrant is beyond the equivalence point. The solution at this point behaves exactly the same as the strong acid, strong base titration. The extra amount of base added after the endpoint will determine the pH, increasing the hydroxide in the solution, making it strongly basic. The strong base is much stronger than the weak conjugate base. Therefore, pH is simply calculated from the excess amount of the strong base. Here's what you have to remember from the previous part, is that 40 milliliters of the sodium hydroxide reacted to neutralize the weak acid. So at this point, after adding 50 milliliters, there's only 10 milliliters of excess base in the solution. So don't make the mistake of assuming 50 milliliters of excess. The first 40 were used to neutralize the acetic acid. So the hydroxide concentration is the concentration. So this is on the top, this is the moles of hydroxide over the volume of the solution. So the concentration, 0.25 molar, times the volume, the excess volume, 10 milliliters or 0.010 liters, divided by the total volume of the solution. So we started with 20 milliliters, and then we added 50 more. So the total volume of the solution is 70 milliliters, which is what you see here, 0.0700 liters. So that gives us a hydroxide concentration of 0.0375. From there, we can find the POH, the minus log of that. We get 1.45, and then subtract that from 14 to get a pH of 2.55. Excuse me, 12.55. All right, here is a titration curve that shows what we calculated in each of these previous parts. We initially found that the pH was 2.5. At the half equivalence point, we found that the pH was 4.74. Of course, that's the point where we added 20 milliliters of the base titrant. At the equivalence point, the volume was 40 milliliters. The pH was 8.98. And then after the endpoint, the pH levels off at 12.55. Okay, so there's our curve. There's a visual curve of each of those points that we calculated along the way. All right, here's example 2 for titration. Calculate the pH of a solution after adding 10 milliliters of 0.0500 molar potassium hydroxide to 40 milliliters of 0.025 molar benzoic acid, C6H5COOH. Ka for benzoic acid is 6.30 times 10 to the minus 5. So I've written the neutralization reaction here where we have a weak acid, benzoic acid, being titrated by a strong base to produce the conjugate base of the weak acid and water. All right, so first let's calculate the volume of the base needed to neutralize the acid. So we have a monoprotic acid and a monobasic base. So we can just say MAVA equals MBVB. And the volume of base that has to be added to neutralize the acid is then found by taking the concentration of the acid, multiplying it by the volume of the acid, and dividing by the concentration of the base. And when we do that, we get 20 milliliters of base must be added to neutralize the acid. Why is that important? It's important because we have to know where are we at in our titration? Are we in zone 1? Are we in zone 2? Are we in zone 3? Okay, and so at the point that 10 milliliters has been added, which is where we are right here, you see how that's half? That's half of 20. So that's the half equivalence point in zone 2, which in example 1, we were able to show that the half equivalence point is special. That's the point at which the pH is equal to the pKa. That's something you should be able to recognize. If you forgot or you can't recognize it, then you could certainly calculate the concentration of the acid and the base after the neutralization occurs, and then use the Henderson-Hasselbalch equation, which is where this comes from. Remember, this is plus the log of base over acid. But at the half equivalence point, these are equal. So this is 1, and the log of 1 is 0. And so the pH is equal to the pKa, or the minus log of 6.30 times 10 to the minus 5, which is 4.20. Example 3, titration. Calculate the pH of the solution after adding 10 milliliters of 0.1 molar HCl to 20 milliliters of 0.1 molar NH3. The Kb of NH3 is 1.8 times 10 to the minus 5. So I've written the neutralization of the weak base NH3 by a strong acid HCl to produce ammonium and chloride ion. All right, so the first thing we need to do is figure out what zone are we in. And the way we do that is by calculating what volume of acid, HCl, is needed to neutralize all of the NH3. So the volume of the acid is the concentration of the base, which is 0.1 molar, times the volume of the base, which is 20 milliliters, divided by the concentration of the acid, which is 0.1 molar. When we do that, we see that the volume of the acid at the neutralization or equivalence point is 20.0 milliliters. So we have to add 20 milliliters of HCl in order to neutralize all of the base. In the problem, we're asked about the pH after adding 10 milliliters, which means that we're below the equivalence point, and in fact, we're at that special point, the half equivalence point. So we have the weak base, NH3, and the salt conjugate, NH4 plus, present in equal amounts. That's a special point in the titration known as the half equivalence point, where the pH is equal to the pKa. Because this is a weak base being titrated, we can find Ka from K water divided by Kb, which is provided. We get 5.56 times 10 to the minus 10. And then pH is equal to pKa, or the negative log of the Ka. Get a pH of 9.26. Example 4, titration. Calculate the pH at the equivalence point when 40 milliliters of 0.0250 molar benzoic acid is titrated with 0.0500 molar KOH. The Ka of benzoic acid is 6.3 times 10 to the minus 5. And we see the neutralization of the weak acid with the strong base here to produce the conjugate base of the weak acid and water in the solution. So first, we're finding the pH at the equivalence point. First, we need to know the volume of the base needed to neutralize the acid. So the volume of the base is the concentration of the acid, 0.0250 molar, times the volume of the acid, 40 milliliters, over the concentration of the base, which we're told is 0.0500 molar. So we have to add 20 milliliters of strong base to this weak acid in order to neutralize it. That's important because we need to know what the total volume of the solution is. So if we start with 40 milliliters of benzoic acid and we add 20 milliliters of potassium hydroxide to get to the equivalence point. At that equivalence point, we have a total volume of 60 milliliters. We need that to calculate the concentrations after at the neutralization or at the equivalence point. So the moles of acid is the concentration of the acid, 0.0250 molar benzoic acid times the 40 milliliters that we started with, right? And when I did this calculation, I got 0.001 moles. Now, remember that at the equivalence point, moles of acid is equal to moles of base. And in this problem, the base is the benzoate ion. All right, so if this is my moles of acid, it's also my moles of base, 1.0 times 10 to the minus 3. Then I can find the concentration of that base at the equivalence point if I divide the moles by the total volume, the 60 milliliters or 0.060 liters. So I get a concentration of the conjugate base at the equivalence point of 0.0166 molar. Okay. Now, I have Ka of the acid. I use that to find Kb, 1.59 times 10 to the minus 10. And the reason is because I can write this Kb expression that says, using this reaction here, I can say Kb is the concentration of C6H5COOH, OH minus, over the concentration of the benzoate, right, at the equivalence point. So after the hydrolysis occurs and the new equilibrium is established, these are unknown concentrations X, which is where I get X squared. And then the benzoate ion concentration is what we calculated here, 0.0166. Sulfur X, which is the hydroxide ion concentration. Find the POH, 5.79, to then find pH at the equivalence point, 8.21. 8.21. Example 5, titration. Calculate the pH at the equivalence point when 40 milliliters of 0.1 molar NH3 is titrated with 0.2 molar HCl if the Kb of NH3 is 1.8 times 10 to the minus 5. So here's the neutralization of the weak base, the strong acid, as we've seen before. And in this problem, we're going to focus in on the equivalence point. All right, first let's calculate the volume and moles of acid required to neutralize the base. So the volume of the acid at the equivalence point is just the concentration of the base, which is 0.1 molar, times the volume of the base, which is 40 milliliters, divided by the concentration of the acid, which is 0.2 molar. So the equivalence point happens after 20 milliliters of acid is added in the titration. Now, the moles of acid at that point are just the concentration times the volume, or 0.0040 moles. And remember that what we're saying here is that the moles of acid equal the moles of base at the equivalence point. All right, so let's think of this as what happens before any of the acid and base reacts what happens at the neutralization and what do we have happening after that. So before anything happens, we have 0.0040 moles of NH3, and if we add the volume to the equivalence point of HCl, we have also 0.0040 moles of HCl. And we start out with no product, right? Now, all of this is going to react. So that we're left with none. But what does it do? It's used to produce our product. And in this case, we're just concerned with the conjugate acid here, right? Obviously, we also will have some spectator chloride ion in the solution, but that doesn't factor into our calculation. So at the equivalence point, we're left only with ammonium and chloride in the solution. And the moles of ammonium produced are equal to the moles of ammonia consumed or neutralized by the hydrochloric acid. And the concentration of that ammonium will be the moles over the total volume. So this is the 40 milliliters that we started with in the flask plus the 20 milliliters that we add to the flask. So we get a concentration of the ammonium ion after the neutralization of 0.667 molar. The conjugate acid that's remaining in the solution, the ammonium ion, is able to dissociate in the water. And so in doing so, a new equilibrium is established, and we need to account for this equilibrium as we determine the pH. So this is production of hydronium ion, so I need a Ka expression, right? NH3, H3O plus over NH4 plus, right? This is dissociation of a weak acid in water. And at equilibrium, some of this starting amount, some of this starting concentration will dissociate into the two products, which we call X, because we don't know how much, right? So if I put an X here and an X here, I get X squared over the ammonium concentration. This I calculated in part in the previous slide. So go back and look at that if you want to. Solving for X, I get 6.09 times 10 to the minus 6, keeping in mind that that's equal to the hydroxide ion concentration. So we can easily find the pH by taking the negative log of the hydroxide ion concentration to get a pH of 5.22 at the equivalence point. I think something I forgot to mention, we're given Kb in the problem, but this is an acid dissociation, weak acid dissociation. So I calculated Ka from Kb to get a Ka of 5.56 times 10 to the minus 10, which I then substituted into the Ka expression to find X. Okay. We've seen these sorts of equilibrium problems before. They all look pretty similar. But at the equivalence point, we get a pH of 5.22. Okay, let's look at a couple of titration curves just to summarize what we might expect to see. So this is a titration. Well, first we'll talk about the titration, summarize as titration of a strong acid with a strong base. And that's the line that we see in black. This is strong acid with strong base. There's a very low initial pH, close to 1, of the strong acid before any base is added. Near the end point, we get this very pronounced, very prominent vertical region near the end point that then levels off just above 12 after the equivalence point. Remember, at that point, the pH is all determined by the remaining strong base. And the equivalence point when a strong acid is titrated with a strong base is always 7. All right, so let's compare in blue the curve of titrating a weak acid with a strong base. Okay. With that black curve we saw on the previous slide. So if we titrate a weak acid, the initial pH before any base is added is above 2. So a little bit higher than when we start with a strong acid. We don't get the same long, prominent vertical region near the end point. It's much smaller, happens much more quickly here. The pH still levels off above 12 after the equivalence point, because again, after the equivalence point, the pH is determined by that excess strong acid. And the pH at the equivalence point is above 7. So in this case, it's closer to 9, between 8 and 9, indicating a strong base as the titrant of a weak acid.